So, when we last left off, we discussed aromatic and anti-aromatic systems, and we talked about the application of frost circles to draw MO diagrams and identify aromatic versus anti-aromatic systems. So, looking at the following molecule, for example, we see that it has 4 pi electrons, and in terms of the orbitals that we're combining to make our molecular orbitals, the orbitals that we are combining to generate our molecular orbitals, we are combining 3 of our p orbitals. So we have 3 p orbitals conjugated in a ring, and we have a total of 4 pi electrons in this conjugated system. So if we wanted to draw a frost circle from this, we draw our ring, we draw a circle around our ring system, and then at each point where our ring touches our ring system, at each point where the ring touches the external drawn circle, we draw an orbital diagram and an orbital at that location with that given energy. So for example, looking at the following diagram, we see that from our frost circle, we have 1 bonding molecular orbital and 2 anti-bonding molecular orbitals. Now, as a consequence of this, when we fill our orbital diagram with our pi electrons, we add 1, 2, 3, 4. We notice that we have a half shell arrangement. So if we have 4 pi electrons, we are filling our anti-bonding molecular orbitals, and we have this half shell arrangement. What does that tell us? Do we have an aromatic or an anti-aromatic system? What can we conclude from this? Are we dealing with an aromatic or anti-aromatic system? Anti-aromatic, exactly right. Because it follows the 4N rule, and as we notice, it also fills the anti-bonding MO, and it has a half shell arrangement. Does that make sense to everyone?
Professor, I have a question.
Yes, please go ahead.
Can you clarify how you knew how many electrons to put on each
So
orbital?
we have 2 electrons from our pi bond, and then 2 electrons from our conjugated lone pair. So for this molecule, we know that 2 electrons are shared. Oh, sorry, 1 moment. So we notice that we have 2 electrons that are shared, and those are shared as part of our pi bond.
Okay.
And then we have 2 electrons that are in a p orbital that are conjugated to our pi system, because this oxygen is sp2 hybridized.
Okay.
Does that make sense?
Yes, it does. Thank you.
Perfect. Any other questions on this example? Okay, so let's work on this example as a group, and I'd like you to predict whether the following ring system is aromatic or anti-aromatic, and then I'd like you to draw an MO diagram to justify your final response. So I'd like to see an MO diagram drawn, and remember you can use the annotate tool to draw out an MO diagram and draw out a molecular orbital diagram on the class whiteboard. So first, I'd like you to tell me, is this aromatic or anti-aromatic? And then I'd like you to justify your answer with a molecular orbital diagram. So let's work on this example for about 3 minutes. And don't be shy to share your responses in the chat or verbally.
Professor?
Yes.
In the 4n rule, is n the number of lone pairs, or?
N is just an integer. It can
Oh, okay.
be 1, 2, 3, 4, etc. So in this first case, when n is equal to 1, we have 4 pi electrons because 4 times 1 is 4.
Of course.
Does that make sense?
Yeah.
Perfect. So looking at this second ring system, what does the class think? Is it aromatic or anti-aromatic? And what does the orbital diagram look like? Remember, you can always access the annotate tool using, there's a set of meeting options when you, in the Zoom call meeting options, one option is annotate, and it allows you to draw out structures. So looking in the chat, we see overwhelmingly that students propose that this is an aromatic system. Students are noting we have 6 pi electrons, so it follows the 4n plus 2 rule. Would anyone like to share an orbital diagram for this structure? Does anyone have a proposed orbital diagram for this structure to help justify and support your answer?
Professor, did you say MO diagram or orbital diagram?
Molecular orbital diagram, just like I drew for this first example.
The one with the circle and the...
Yep.
Okay.
That's a frost circle, which allows us to describe and draw out our molecular orbitals with the correct relative energies. And then from the frost circle, by filling the frost circle, you can get a sense of bonding versus anti-bonding interactions, and then assign your ring system as aromatic or anti-aromatic. Does that idea make sense? One thing to keep in mind is that the ring should be arranged so that the single vertex is pointing down. So just rotate your ring 180 degrees. So the oxygen is pointing down.
Oh, okay, got it. I think I'm just going to give up. It's kind of hard to do with my keypad.
Would anyone like to share a response? Would anyone like to share a drawing for this MO diagram using the annotate tool? Okay, so let's discuss this example and let's unpack this example. So if we think about our 5-membered ring, so we draw our ring system and we draw our frost circle surrounding our ring system. We have 5 molecular orbitals arranged as follows. So in turn, we have 3 bonding and 2 anti-bonding. So we know that in this ring system, we have 2, 4, 6. We have 6 pi electrons. So when we fill our molecular orbitals with our pi electrons, we have 1, 2, 3, 4, 5, 6. And as we notice, we have filled our bonding molecular orbitals. So we have a full shell arrangement where we've completely filled our bonding molecular orbitals, so then we can conclude that this ring system is aromatic. Does that idea make sense to everyone? Does this idea seem familiar to everyone? Okay, so we can conclude then that this bottom ring that we call furan is more stable than this quite strained epoxide. Does someone have a question that I can address?
I have a question.
Yes, please go ahead.
So I'm like confused on how you know that there's only bonding electrons to fill in the diagram.
Well, if we have 6 pi electrons, right? We use our 6 pi electrons to fill in our molecular orbital diagram for our molecular orbitals generated from our various p orbitals, right? So we take our component p orbitals, we combine them together to get a series of molecular orbitals, and we fill our molecular orbital diagram with our pi electrons. So since we have 6 pi electrons, we add 6 electrons to this diagram, and we conclude that we filled our bonding molecular orbitals.
Okay.
Does that make sense?
Yes, thank you.
Perfect. So the reason why it's drawn upside down, so to answer that question, essentially the reason why it's drawn upside down as a general rule is generally when you derive this MO diagram, your molecular orbitals are arranged symmetrically about 0 energy, and it just so happens that when you have an odd number of orbitals, you try to arrange it in, well, let me phrase this as, you will try it will try to adopt an arrangement that minimizes the energy of the electrons that are occupying the molecular orbitals. And in this case, we're able to maximize our stabilization by placing our electrons in these bonding MOs compared to other arrangements. Does that make sense? So essentially, this arrangement of orbitals gives us the lowest overall energy for this 6 pi electron system. Any other questions on this example? Okay, so why is this important? Why does this matter? Well, we often encounter aromatic systems in the form of aromatic ions. So what's so special about aromatic ions? Well, our 4n+2 rule for aromaticity applies to ions just as easily as it applies to neutral species. So both the cyclopentadienyl anion and the cycloheptatrienyl cation are aromatic, right? Both of these systems have 6 pi electrons, right? So we have an anion that's aromatic and a cation that's aromatic. So both this anion and cation contain 4n+2 pi electrons in a ring of continuous p orbitals. So does everyone see how we can have aromatic ions? Does everyone see how aromaticity can just as easily apply to ions? So building on that idea, if we wanted to justify our answer and draw out an MO diagram, for example, the cyclopentadienyl anion, this reminds me a lot of furan. So if we draw out our MO diagram, it will look almost identical to that of furan. We have 6 pi electrons, 1, 2, 3, 4, 5, 6. So we've maximized our bonding interactions while minimizing our anti-bonding interactions. So the cyclopentadienyl anion, it's a pretty straightforward analogy to the furan example. But looking at the cycloheptatrienyl cation, so this time we may have to draw out a formal Frost circle. So we drew out our ring, we've enclosed it in a circle, and at each point that our ring touches the circle, we draw an orbital at that given relative energy value. So we end up with an MO diagram that looks something like this. And in turn, considering we also have for our cycloheptatrienyl cation, we also have 6 pi electrons. That in turn tells us that we need to fill this molecular orbital diagram with 6 pi electrons. So then we fill this diagram 1, 2, 3, 4, 5, 6. And as we can see quite clearly, we have maximized our bonding interactions while minimizing our anti-bonding interactions or minimizing our filled anti-bonding orbitals. Does that make sense? Okay, so when in doubt, you can make an MO diagram and justify to yourself that you have a full shell versus a half shell. So why is this aromaticity important to consider? Well, 1,3-cyclopentadiene contains a set of conjugated double bonds joined by a methylene group that blocks delocalization. If we try to ionize cyclopentadiene via removal or loss of hydride, if we wanted to make the cyclopentadienyl cation, this system has 4 pi electrons and it's anti-aromatic. As a result, the cyclopentadienyl cation is difficult to form. Conversely, if we try to remove a proton in the presence of base to make the cyclopentadienyl anion, which has 6 pi electrons, this process is very easy because when you remove your proton, you end up generating a very stable aromatic ion. So, because acid strength depends on the stability of our conjugate base, we can conclude then that, and we can see pretty clearly, and we can pretty clearly explain why cyclopentadiene is abnormally acidic. This proton has a pKa of somewhere around 16. And the reason why this proton is so acidic is because when you remove that proton with a base, you end up generating an aromatic, very stable cyclopentadienyl anion. Does this question make sense? Does this idea make sense? Any questions on this idea? Okay, so our takeaway from this is that aromatic ions are especially stable and are more easily generated. Conversely, anti-aromatic ions are especially unstable and are more difficult to generate. So this has a direct impact on many common patterns of reactivity, such as protonation or deprotonation and loss of groups as part of ionization. So, looking at another example where we compare and we look at an acid-base reaction where aromaticity plays a substantial role in the acidity and basicity of our compounds, let's look at pyridine and pyrrole. So in both cases, we start off with an aromatic system. Both of these systems have 6 pi electrons. Okay, so from here, when pyridine undergoes an acid-base reaction, we generate a pyridinium ion. Is this product here, is this product aromatic or anti-aromatic or neither? For pyridine, is the conjugate acid product of pyridine aromatic, anti-aromatic, or neither? What do we think? So counting, we have 2, 4, 6. If we have 6 pi electrons, what does that tell us? So for the pyridinium ion, 6 pi electrons, what does that tell us? Is that aromatic or anti-aromatic? If we have 6 pi electrons, does it follow the 4n plus 2 rule? We can conclude that this ion, this conjugate acid, is aromatic. So when we protonate pyridine, we do not disrupt aromaticity. Comparatively, if we start with pyrrole, for example, and we protonate pyrrole, looking at this product, this conjugate acid of pyrrole, is this species aromatic, anti-aromatic, or non-aromatic? So you're on the right track. You counted 4 pi electrons, that's correct. But is this system completely conjugated? If we look at this molecule, is this system completely conjugated? Is there a set of p orbitals conjugated present on all atoms in our ring? Is this a continuously conjugated system? What do we think? No. So then it's not anti-aromatic, rather it is non-aromatic because it doesn't have a fully conjugated pi system in the ring. Does that make sense?
And what is the difference between non and anti-aromatic?
So anti-aromatic is a system that contains a contiguous set of conjugated p orbitals arranged in a ring and has 4n pi electrons. Because in this case, when we look at the conjugate acid of pyrrole, this species has an sp3 atom. This nitrogen is sp3 hybridized. It does not have a contiguous set of p orbitals, so it's neither aromatic nor anti-aromatic. We call it non-aromatic. Does that make sense?
Yes, thank you.
Perfect. So then, what can we conclude from this? Well, we see very clearly that protonation of pyrrole breaks aromaticity. We can conclude that this non-aromatic system is not very stable. It's not like actively unstable like an anti-aromatic system, but it certainly doesn't get any benefit from it doesn't receive any stabilization from aromaticity because this ring is non-aromatic. Pretty straightforward in that idea. So then, protonation of pyridine breaks aromaticity. So then, which of these reactions, which of these protonation reactions it occurs more readily? In which case do we have a small difference in energy between our reactant and product? So we have one student typing in the chat that this second reaction occurs more readily, and that's exactly right. So the conjugate acid of pyrrole is not aromatic and in turn is less stable than the parent base pyrrole. Pyridine and its conjugate acid are both aromatic, so protonation of pyridine is more facile and it occurs more readily. So a key thing I want you to keep in mind, when you disrupt aromaticity, when you break aromaticity, especially via a protonation step, you in turn limit the basicity of that lone pair if it's participating in conjugation, or you make your molecule less likely to undergo protonation or reaction if it breaks aromaticity. Does that idea make sense? Does everyone see why pyridine is more basic? Because you can use the lone pair for acid-base reactions without breaking aromaticity. If you try to use the pyrrole lone pair for acid-base chemistry, you end up generating an sp3 nitrogen that's non-aromatic, not very stable, and as a result, it's much more difficult to protonate pyrrole, and it's much more difficult for pyrrole to engage in these acid-base reactions. Does that make sense? Okay, so let's keep going now. And I'd like you to answer the question, which of the following compounds is a stronger base? And it's important to think about it in terms of differences between your base and the conjugate acid. So I'm drawing out these conjugate acids, and what do we think? A or B? What is the stronger base? What do we think is the stronger base? A or B? And for those who are answering A, would you be able to provide a justification why? So if we think about what makes a strong base, right? So a strong base, the lone pair is generally, so if we have a strong base, as a review from chapter 2 of Chem 112, a strong base generally has a localized lone pair, and strong bases also have very weak conjugate acids. So if we think about this protonation step, for a moment, in which, if we think about the protonation of pyrrole, does protonating pyrrole break aromaticity? Does protonating pyrrole break aromaticity? Yeah, so protonation of pyrrole breaks aromaticity. And as a result, would you expect pyrrole to be a very effective base? Is this protonation very favorable if it breaks aromaticity? It would not be, right? So protonation is not favored. And as a result, A or B, which molecule is the stronger base? Which molecule is the stronger base? If protonating pyrrole, which is structure A, is not very favorable, what does that tell us if we compare to structure B? If A is not a very effective base, while B has this nice isolated lone pair on nitrogen, in turn we can conclude that B is the stronger base. Does that idea make sense? Any questions on this example? Does this make sense to everyone now? Okay, so I'd like us to apply what we've learned to the following example, and I'd like you to tell me which proton, A or B, is more acidic. You will need to draw each conjugate base, and you'll need to draw an MO diagram, at least for the cycloheptane ring, to justify your answer. So let's take about 4 to 5 minutes to work on this example. And don't be shy to share your proposed responses in the chat verbally or using the annotate tool. So let's work on this example, and don't be shy to share your thoughts in the chat verbally, or of course with the annotate tool. As this problem asks for us to draw an MO diagram for the cycloheptane ring system. Of course, the cycloheptane ring system that's given in this problem. I'd like to see a sample MO diagram so I can get a sense of how the class is tackling this problem and any feedback that I could possibly provide. Does everyone understand what we're doing right now? And are there any questions that I can answer about this problem? Any questions on this example? Okay, so we have the conjugate base anion drawn. Let me redraw what was presented just so that way we can discuss it in a little bit of detail, but that looks exactly reasonable. So the structure drawn by the student who shared their annotation. 1, 2, 3, 4, 5, 6, 7. Let me draw it this way. 1, 2, 3, 4. Okay, perfect. So this is the following conjugate base anion. Would someone like to share an MO diagram for the conjugate base anion of A? Looking at both of these structures and looking at the conjugate bases, which of these two conjugate bases, when we draw them out, which of these two conjugate bases are aromatic, anti-aromatic, or non-aromatic? Does that make sense? So what does the class think on this? What does the class think about this? So if we have the conjugate base of A drawn, would someone like to share a drawing for the conjugate base of B? And then from that information, can we figure out whether these conjugate bases are aromatic, anti-aromatic, or non-aromatic? Do we have the tools to do that? Yeah, we do. By counting our pi electrons, we can determine whether it follows the Huckel rule or whether it is anti-aromatic. So we have a student sharing their proposed conjugate base structure. It looks reasonable to me. Yep. So I'll transcribe this structure. But that structure drawn was perfect, perfectly reasonable. So now that we have these two conjugate base anions, sorry, the Huckel rule is the 4n plus 2 rule. It's essentially an aromatic system has 4n plus 2 pi electrons. Did that answer the question in the chat? Perfect. So looking at these structures, and if we count our pi electrons, which of these structures are aromatic and which of these structures are anti-aromatic? So we have a student noting that the structure on the left has 8 pi electrons. That's right. Yep, so we have 8 pi electrons. This does not follow the 4n plus 2 rule. Instead, it follows the 4n pattern of pi electrons. So when we have 8 pi electrons, we can conclude, as the students are noting in the chat, that it is anti-aromatic. So this ring system is anti-aromatic. For B, yes, there's a negative charge centered on the lone pair. Yep, exactly right. Comparatively, looking at B, we have 6 pi electrons, and as a result, it follows the 4n plus 2 rule. And as a result, what can we conclude about B? What can we conclude about the conjugate base of B? Is it aromatic or anti-aromatic? What can we conclude? The conjugate base of B is aromatic. So in this case, which of these protons is easier to remove? Which of these protons is easier to remove? Which of these protons, when removed, gives us an aromatic system? Which of these protons, when removed, gives us an aromatic system? B, right? So we conclude that proton B is more acidic. As removing proton B gives an aromatic stable anion. Does that logic make sense?
Professor, I have a question.
Yes, please go ahead.
So it says in here to draw an MO diagram for the cycloheptane ring system.
Yes. Yep.
Like, did we do that here?
Not
Because
yet.
I don't. Oh, okay.
Yep.
Are we gonna do that?
Yes, we will.
Okay, thank you.
Yep. I just want to make sure everyone's comfortable with this first premise before we discuss how can we prove to ourselves that structure A, this anion, is anti-aromatic.
Okay, thank you.
Is there any way you could draw the mechanism for deprotonating?
Sure. So if we have a base, I was drawing the arrow. So if we have a base, it would abstract the proton. The protons shared in this carbon-hydrogen bond would then end up localized on the carbon atom, and that's how we generate our aromatic anion. Does that make sense to everyone? So the base
Yes.
is one pair, abstracts a proton, and we generate our conjugate base anion. So to justify and to look at the MO diagram for structure A, so to unpack this structure a little bit. So we know we have 8 pi electrons, and drawing out a frost circle, we have 1, 2, 3, 4, 5, 6, 7 orbital placements. We then fill our molecular orbitals with our pi electrons, 2, 4, 6, 8. We notice that we first have a half shell arrangement, and second, we are filling our anti-bonding molecular orbitals. And in turn, these interactions are very destabilizing. So having a half shell or a half filled highest occupied molecular orbital is a very destabilizing interaction, and filling these antibonding orbitals heavily destabilizes our molecule. Does that make sense?
Professor, how did you like determine the line that divides the anti-bonding and bonding MOs? Is it just
Generally,
directly across?
they're divided symmetrically about 0 energy. Yeah.
Okay, thank you.
Mhm.
I know you already said it already, but why did you draw it upside down again?
So it's essentially because when we try to arrange our electrons into our bonding and antibonding molecular orbitals, we're trying to optimize for the lowest possible electron energy for each of our structures. And when you have an odd number of molecular orbitals, it becomes preferential to try to place as many electrons as possible in as low energy bonding MOs as possible.
Okay, I see.
Does that make sense?
Yes, thank you.
So the reason this asymmetry in turn means that even though the antibonding MOs are higher in energy, the bonding MOs are lower in energy on average because if we add up all these energies, they should cancel out to 0. Does that make sense? So like if we added up if we looked at the average of all of our MO energies, it would average out to 0. That's why all of these orbitals are centered about 0 energy. Does that make sense?
Yes, thank you.
Okay, perfect. So we can conclude from this orbital diagram that we have an antiaromatic anion for the conjugate base of A. Let's take a look at another example. So generally the aromatic species is preferred over the non-aromatic or anti-aromatic species. This often comes up when we start to talk about tautomers of phenol. So tautomers are structural isomers that can be interconverted via a proton transfer. So looking at these two structures, which of the following tautomers is more stable? So which of these two tautomers is more stable? And really try to think about this in terms of aromaticity. So which of these two tautomers, A or B, is more stable? What do we think? Which of these tautomers is more stable and lower in energy? Anyone have a proposal? So we have a lot of students saying A. What's special about A? What's really a standout feature of A? What's special about A? And well, not beyond just more conjugation.
It's aromatic.
It's aromatic, exactly. So A is an aromatic system, and this aromatic ring is quite stable and low in energy. If we compare to structure B, is structure B aromatic? Is structure B aromatic? No, exactly right. It's non-aromatic. Yep. The responses in the chat look perfectly reasonable. A and B can be interconverted via a proton transfer, where the base removes a proton and then a trace amount of acid donates a proton. This is known as a tautomerization reaction. However, if we look at these two structures, is this equilibrium going to be 50-50, or will this tautomer equilibrium, will this tautomeric equilibrium favor A or B? Which species is favored at equilibrium? How should we draw our equilibrium arrows?
The arrow going to the, or pointing towards A would be bigger.
Yep, exactly. So A is favored at equilibrium. And this is important to consider because phenols don't react like ketones. And it's important that when you draw your structures, you give the best depiction of the structure as it actually is. So it would be odd to draw this structure with the ketone tautomer present. Does that example make sense to everyone? Any questions on this example?
Professor, I have one quick question.
Yes, please go ahead.
By like favoring, isn't that like the same as Le Chatelier? Like, does it have a relation?
So Le Chatelier is related to equilibrium and what happens when you perturb an equilibrium. This is if we establish the tautomers are often in equilibrium with each other in solution. And in this case, the phenol tautomer is preferred over the keto tautomer. Does that make sense?
Yes.
Perfect. So A, in terms of pi electrons, when we are looking at aromaticity or anti-aromaticity, you only count the pi electrons that are directly associated with the p orbitals conjugated in the ring. Not with the ring, but conjugated in the ring. So in this case, we have 6 pi electrons in phenol. Does that make sense? Perfect. Perfect. So let's keep going now. And when we start to talk about aromatic systems, and when we talk generally that the aromatic species is preferred over the non-aromatic or anti-aromatic species, when we start to look at resonance contributors and cationic character, one thing that we notice is that if a structure can generate a cationic or anionic resonance structure that is aromatic, that structure will have a greater contribution to the resonance hybrid, to our actual structure. You can see this experimentally in the bond lengths, as well as the cationic or anionic character of atoms in our structure. So for example, if we look at these two different resonance forms, they're resonance forms. They're not things at equilibrium. They're two different resonance structures for the same compound. My question to all of you is, which of these two resonance structures is aromatic? Which of these two structures is aromatic? So I'll label them A and B. Which of these two structures is aromatic that follows our 4n+2 rule for pi electrons in the ring?
Would it be A?
So looking at A, so the ketone pi electrons aren't considered as part of the ring. So when we count for determining aromaticity or anti-aromaticity, we only count the electrons in pi systems that are directly conjugated in the ring. So for example, if we look at B, we notice it has 0 plus 2 pi electrons. So if we have 2 pi electrons, what does that tell us? Is that aromatic or anti-aromatic?
Aromatic.
Yep, 2 pi electrons is an aromatic system. And in turn, we can conclude that B is a large contributor or a larger than usual contributor to the overall structure. Now, what does that mean? What relevance does that have? Well, if you think about B for a moment, if you think about it really carefully here, when we have our motif B, we know that on average, if we look at our carbon-oxygen bond, we know that this bond will have more single bond character because the structure with a single bond is a major contributor. And we'd notice that we'd have a lot more localized charge or a lot more built up partial charge on our two atoms involved in the carbon-oxygen bond, because this resonance structure that is aromatic exhibits a stark separation of charge. So B is a larger than usual contributor to the resonance structure, and in turn, it directly impacts the bond length and strengths observed in our overall structure. Does that idea make sense to everyone? Does that idea make sense? Okay, so let's keep going with this. And we'll take a look at the following pair of resonance structures. And I'd like you to tell me which of these structures, A or B, is the most major contributor. Which of these structures has the greatest contribution to our overall structure?
Is it A?
So one student's proposing that A is the major contributor. And would you be able to provide an explanation for why?
Okay, wait. Now that I'm looking at it, well, I was thinking because it would have 6 pi electrons, but
So you're on the right track, but think about it using the similar line of logic, but from a perspective of, are any of these structures anti-aromatic? So this
okay.
ketone isn't counted as part of the pi electrons. You only count electrons conjugated in the ring. But if we look at structure B, what's so interesting about structure B? What's so special about it? In a bad way.
And is it anti-aromatic?
Yes, anti-aromatic, right? We see that in this structure, for this ring here, we have 4 pi electrons. So as a result, this resonance structure B is a very, very minor contributor. And as a result, if we looked at this carbon-oxygen double bond, this carbon here would be not very electrophilic. So it would be difficult to engage this carbonyl carbon in typical reaction with nucleophiles. This carbon will be a little bit more resistant to reaction than usual. And that's because this contributing resonance structure, where there is cationic character on our carbon, is a very, very, very minor contributor. Does that make sense?
So does A only have 4 pi electrons?
So since it's conjugated with atoms outside of the ring, you can't really count your electrons and say this is definitive, this is aromatic or anti-aromatic. A would fall into the category of it's neither, because it doesn't meet the criteria where we have all of our p orbitals within the ring fully conjugated, and we have, for example, 4n plus 2 pi electrons conjugated in our ring. What we can do is we can look at our different resonance contributors and draw conclusions about their stability. Does that make sense?
Yeah, I was just thinking like where the double bond to the oxygen converges with the ring, I was thinking of that as like counting as a pi electron for some reason.
I certainly can see why you could think that, because when you think about conjugation, this ketone is conjugated with this ring. But when
Okay.
we're talking about aromaticity or anti-aromaticity, we're looking at a ring system, we're making sure it's fully conjugated, we're counting the number of electrons in that ring system, and if there are a certain number of electrons in that conjugated ring system, it's aromatic, and as a result, it's especially stable. Does that
Okay.
make sense?
Yes. Thank you.
Perfect. Any other questions on this example?
I got a question.
Yes, please go ahead.
Oh, for the second one, it doesn't matter if the negative charge is in the most what you call that, electronegative element, because it's not participating technically on the ring, right? So it cannot be considered a major.
The location of the negative charge, or rather the location of the lone pair, is important. And it partially explains why, like, a contributing structure that looks really weird, something like this, actually has more weight than it would normally. Of course, it doesn't follow the octet rule, so it breaks that convention. But this contributing structure has more weight than you would expect because this ring system has 6 pi electrons and is aromatic. So the location of the lone pair is important because in some cases you can end up with preference for one arrangement or distribution of electron density. So to give another common example, if you fuse, for example, a cyclopentadienyl system to a cyclopropenyl system, we notice that there is a preferred arrangement of electron density for this double bond. Would someone like to take a guess? Would I prefer to push my electron density to the left towards my 5-membered ring, or to the right towards my 3-membered ring? What do we think? Left or right?
Will it be right?
I was gonna say left.
So let's look at our 2 options.
Left.
So let's entertain our 2 options. So if we pushed it to the right, we'd end up with a structure that looks something like this. So we have a lone pair here, and we have a cation here. So are the ring systems that we're dealing with here aromatic or anti-aromatic?
Anti.
Anti, yep. So if we pushed our electron density in this double bond to the left, we'd end up with the following structure. Whoops. And in this case, both of our ring systems are aromatic. So this structure actually has a very large dipole moment. Abnormally large for something that only has carbon and hydrogen atoms. And it's due to the fact that this double bond is highly polarized, because when we polarize our double bond, we would generate an aromatic ring system. This resonance structure, which has 2 aromatic rings associated with it, is very, very, very highly contributing. And as a result, our actual molecule exhibits a structure closest to that of this resonance structure. Does that make sense?
Yes. Thank you so much.
Professor,
Does anyone have the problem number similar to this? I know that this is a very common example brought up, and I would check in the back of the book in chapter 15. 15.17 is something similar to this. Yes, there was a question in the chat. Yes, please go ahead. Was someone talking?
yes. So for the previous example,
Yes.
why isn't A considered to have 2 pi electrons?
So it's because this double bond is conjugated with our ring. And when you're thinking about deciding whether a ring system is aromatic or anti-aromatic, you need to make sure that all the atoms in the ring are conjugated and there's no external conjugation that affects your electron count. So in A, you can't really say that it has 4 or 2 electrons in the ring itself because this double bond is connected to atoms outside the ring. Does that make sense? So the
Yes.
definition of aromaticity and anti-aromaticity are very specific. It's for a cyclic system that's fully conjugated that has a certain number of pi electrons. When you start to get conjugation outside of your ring, it's tricky to say whether that system is aromatic or anti-aromatic. And we can look at the resonance contributors to get a sense of the true sort of distribution of electron density in our molecule. Does that example make sense?
Yes, thank you.
Perfect. So let's look at another example, and this is one that's pretty common, and it's pretty surprising actually when it leads to a very non-intuitive result if you aren't considering this idea of aromaticity. So we know that aromatic ions are especially stable, and anti-aromatic ions are especially unstable and are difficult to generate, right? So if we think about SN1 reactions and cation formation, for an SN1 reaction, so like if you have like an alkyl chloride and you treat it with an alcohol, the first step is loss of our leaving group to make our cation, and then we attack it with our nucleophile, right? This is a textbook SN1 mechanism. Now, this first step is the loss of leaving group is rate limiting, right? So if it's difficult to generate a cation, it'll be very hard for us to engage in an SN1 reaction. So for example, if we compare these two molecules and we ask ourselves which of the following substrates react faster via the SN1 reaction, would anyone have a first guess, A or B? What substrate will react faster? Which substrate will make the more stable carbocation? Which structure will make the more stable carbocation when chloride leaves? What do we think, A or B?
Would it be A?
So would you be able to offer an explanation why? So if we make the following cation, is this cation especially stable or unstable?
Would it be stable since it's in secondary?
Yes, that's one thing to know.
And it's also
And it's aromatic.
Aromatic, exactly right. So we're generating an aromatic cation, and as a result, this cation is especially stable. Does that make sense? Comparatively, if we look at structure B, this cation, it's conjugated, but it's non-aromatic. So the cation from A is more stable. As a result, because cation A is very stable, A will react readily via a SN1 reaction. Does that make sense to everyone? Does this idea make sense?
yes.
Well, B is non-aromatic because is this ring fully conjugated? Is the ring fully conjugated? Does it have a set of contiguous p orbitals or a fully conjugated pi system? As we see, we have some sp3 atoms that break conjugation. And as a result, it's non-aromatic. So the cation that we make is less stable. So the rate of SN1 reaction is going to be slower because our rate limiting step has a higher barrier. Does that idea make sense? Does this example make sense?
Yes, it does.
Okay, so then Let's look at the following case. And this is an example that often catches students off guard if they aren't thinking carefully about this problem. So which of the following substrates reacts faster via an SN1 reaction? Which of these substrates react faster? And why? I mean, if we compare A and B, A looks, that's pretty conjugated. That's pretty conjugated. But there's something a little awkward about A. So I see a lot of students frantically typing in the chat that they think B reacts faster. Would someone care to offer an explanation why? So if we lose our leaving group and we make our carbocation, what is a problem with A?
It's anti-aromatic.
A is anti-aromatic. And as a result, cation A is very unstable and difficult to generate. That in turn leads to a slow SN1 reaction. Functionally a non-existent SN1 reaction. So in fact, you can do some pretty weird stuff with that rule in that if you take these substrates and you install a stereocenter, this is probably the only time that you're going to be able to get away with doing like a substitution reaction with like equivalent of alkoxide via an SN2 process. This is one of the few of allylic alkyl halides that will actually react via an SN2 process. Yes, A is anti-aromatic because we have 4 pi electrons. Yeah. So as you can see, this idea of aromaticity and anti-aromaticity pops up in examples that may seem almost a little pre-packaged at first glance, but are more common than you would expect. So when you deal with these anti-aromatic intermediates, it's very difficult to generate anti-aromatic systems, and as a result, that increases the activation energy for this substrate to engage in SN1 reactions. So then, when you think about mechanisms, it's important to consider the nature of your intermediates. And aromaticity and anti-aromaticity is another tool, another part of that consideration. Does that make sense to everyone? Did that answer the question? Okay, so let's keep going now. And let's talk a little bit about polycyclic aromatic compounds. So aromatic compounds can have rings that share a set of carbon atoms, fused rings. So compounds from fused benzene or aromatic heterocyclic rings, are they themselves aromatic if they contain 4n plus 2 pi electrons? So these are some examples: naphthalene, anthracene, benzoate, pyrene, coronene. All of these are polycyclic aromatic compounds. So that's all I have for chapter 15. Given that we only have 9 minutes, what we're going to do is, if it's okay with everyone, we'll take our 10-minute break before lab a little bit early, and then we'll resume with a lab lecture from the chapter 13 notes. So we finished chapter 15, and we're going to take a quick break, and then we'll resume with a discussion of the chapter 13 notes. Does that make sense to everyone what's happening at this time? So I'll pause the recording and we'll resume